Okay, I'd like to briefly review what we did in class and then talk about how to extend it. So we talked about a way of looking at a matrix multiplication in a special case where we start with just a column matrix, which is a matrix with exactly one column, and also a row matrix, which is a matrix with exactly one row. So what we want to think about is this column matrix as some kind of pattern, and the row matrix is the activations of that pattern. So when we multiply the two, what we see is the numbers in the row matrix tell us how much this column is activated at every instant in time. So we're really thinking here about the rows as being frequencies in a spectrogram, and the columns as corresponding to windows. So B gives us the activation of these little spectral patterns. So this is like a single window. That's the way you think about it. So what I showed you was, okay, let me load in a little window of Prince's voice that I extracted from One Dove's Cry, and then the drums from that tune. If I create a single window from the voice and a single window from the drum, they look like this. And so this is actually, each one of these is just a single column. So this is a column vector, just this single window. So we can think of that like our A matrix. So now let me create some activations where I say, okay, every 10, well, let's make them every 20. Every 20 windows, I'm going to have a 1. And the rest are going to be 0. So what that's saying is I'm going to repeat this, whatever this is, I'll make it the voice here. So the voice is the column matrix. My activations are mostly 0, except every 20 it's a 1. So every 20 I'm going to have this voice window. And so the activations look like this. They look like a comb filter, actually. And the resulting spectrogram looks like this. So you can see that it's mostly quiet, but then that voice repeats itself every so often. And it sounds like this. So, and I also showed how, well, you don't have to just have the same number for every time it's activated. You can actually have that number be decreasing over time. So, whoops, let me make this a little bit longer. So yeah, you can have that number be decreasing over time, so it gets quieter and quieter. Okay, but the point is just, you think of the row matrix as an activation matrix, and you think of the column matrix as your sort of sonic template, single window of spectrogram. So then I showed you that, okay, yeah, well, here's the same thing with the drum. And then I showed you could do this 4-on-3 rhythm by creating a template where, or an activation pattern, a row matrix, where every 20 samples is a 1 and every 15 samples is also a 1. That will make a 4-on-3 pattern. So the 4, this will repeat itself 4 times for every time that this repeats itself 3 times. The total period of a measure of this rhythmic repetition is 60. So if I do that, I hear this nice, so this is what it looks like, the row matrix. It looks a little weird, but when I play it, I hear this nice pattern. Okay, now I just want to extend this a little bit and actually make it so that that the 3, every time the 3 repeats itself, so this period of 20, I want to make that the voice, and I want to make the other one the drum. So what I could do is do this twice. So I'll first make an H. Okay, so the 4 is the drum, so I'll say V is equal to S drum.H. But then let me make another one. I'll say H is equal to MP.0. So maybe I'll say this is H1. And actually, I won't do that until the end. Okay, so then let me say H2 is equal to zeros, 1, 500, H2, 0, 0, 15. So every 15, I'm going to make H2 a 1. And so now let me say that the spectrogram, the multiplication of the 2, should be let's see, I said the 3 is voice. Okay, so I'll say s voice dot h1 plus s drum dot h2. So we can do that. Okay, so now we can hear that. But actually, there's a more elegant way to do this with a matrix multiplication, where our first matrix is actually, instead of being one column, it's 2 columns, and our second matrix is 2 rows. So let me show you what I mean. So I'll say s both is equal to np.concatenate s voice. Okay, let's see. I'll make voice be the first column. I'll make drum be the second column. So let me just show you. Actually, I'll plot this. I'll go up and grab some of this plotting code. Okay, so now I have a matrix with 2 columns that I'm calling S both. The first column is the voice and the second column is the drum. Now guess what I'm going to do? I'm going to create a matrix with 2 rows. So I'll say H is equal to np.zeros, 2 rows, 500 columns. Okay, now the first row is going to correspond to activations from the first column. So if I say H first row, and what did I do? I said every 20. Okay, so first row corresponds to activations of first column. Cool. And then I'll do the second one. So here's the second row. Second row corresponds to activations of second column. And now I can do something much more elegant. I can say that V is simply equal to a single matrix multiplication, which is S both dot dot H. All right, so now let me go ahead and listen to that, make sure I get the same thing. Right, so good. All right, so now we're going to think in this framework. Let me show you the activations. Just so you can see what I mean. Oops. Okay, so now you can see this is a matrix with 2 rows. The first row corresponds to the activations. Oh, something looks a little funky here. Hang on. Equals, let's say, I think it may be aliasing. Yeah, okay. Okay, there we go. So anyway, we see that the first row has 3 beats for every 4 beats of the second row. The first row ends up being the voice, because that's what I made the first column be of the matrix A. And then the second row corresponds to the drums. So this is almost like a musical score. You can look at it that way, almost like sheet music. This is telling when the moments when the voice is supposed to go, and this is telling when the moments when the drum's supposed to go. All right, so I'm going to have you do just a little exercise on that to make sure that you're following. And then we will use this to do the reverse, which is starting with regular audio. Can we actually decompose it into these 2 kind of matrices? Okay, so we'll do that in a moment.